All right, so mass is this measurement of inertia, right? The greater the mass, the more inertia an object has, right? It's like, if you were trying to move a, 50-pound rock versus moving 100-pound rock, right? You got to apply a lot more force to move the 100-pound rock. That's the idea of inertia. All right, so mass is measured in units called kilograms. In general, sometimes we'll measure stuff in grams, in the laboratory and so forth. But generally, in the equations we're about to use, we're going to use kilograms. Um, However, mass will often be confused with weight. It's not weight. Weight is actually a force, and a force is different. It is a different thing unto itself, right? Forces can cause acceleration. Forces can add up to not where there's no acceleration. Um, all right. So, for example, gravitation is a force. Weight is also a force. Um, all right. So, let's see. And this is actually a really good statement right here. Weight can change from place to place, but mass doesn't. So, if you take a rock and you put it on the moon, it weighs a lot less because the gravity of the moon is a lot smaller than it's about 1/6 the gravity on Earth. You take that same rock and you put it on Mars, and it weighs less as well. It weighs more than it does on the moon because the gravity on Mars is about 1/4. Um, you know the weight. So like for example, you take 100 pound, you know, 100 pound rock on Earth and you put it on Mars, it would weigh about 25 pounds. This idea of weight varies from location to location. And of course, you can be weightless as well, which means you're so far away from a very large mass that you don't feel any. Weight is really a consequence of gravity, of the gravity when you're on a planet or close to a planet. If you're far enough away from the planet, you don't really feel any weight, or you actually feel what's sometimes called, like the astronauts in the International Space Shuttle feel, the International Space Station feel what's called microgravity, right? So, and sometimes people you just say, oh, they're weightless. They feel really almost no weight at all. That's really what's going on. Right. Anyhow, but however, whatever their mass is has not changed. All right, so this is truly Newton's second law of motion. We're not really going to use this that much. This is kind of just getting us. This is what we use to understand some of the equations that we're about to encounter for astronomy. All right, so the acceleration is equal to whatever the net force. This has to be, F has to be the net force divided by the mass. So more massive objects will get a smaller acceleration, right? Because they're inversely proportional to each other. As the mass goes up, the acceleration goes down, right? For a given force. And again, it's got to be the net force, right? So you can't, you can have many forces adding up to zero, and then if the net force is zero, the acceleration is zero. All right, so that's like I said, we're not going to really use this equation. This is more of a physics equation. We use this in physics all the time, and we perform experiments using it. But this is showing us the consequence. The consequence of this equation will lead to some astronomy equations. I guess that's what I'm trying to say. All right. So that's the equation in words. We're interested in gravity, right? And that's the primary force in all of astronomy is gravitation. So here, this is a good example of Newton's second law of motion, right? So let's say you have an empty shopping cart, you apply a force to it, it accelerates, right? The red here is the acceleration. So if you apply the same force to a shopping cart that is loaded with a bunch of stuff, imagine like there's a bunch of water in there or something like that. Like you got cartons and cartons of water. Or a lot of water. Okay, if you apply the exact same force, you're not going to get the same acceleration. You're going to get much smaller acceleration, right? Because the mass of what you're pushing on the cart plus all the stuff inside it is greater than it was up here. Just an empty shopping cart. All right. So the third law. Okay. So the third law is it's kind of a strange law. So if you it actually leads to another concept called momentum. That's really what the third law is all about. And in this concept of impulse. Right. So here's the idea of the third law. Like if you just go and you push you push on the wall, you got a wall next to you, push on it, the wall actually pushes back on you with the exact same amount of force. That's the third law of motion. Right? And I know it's kind of a strange thing. You might, one of the typical questions they ask in physics, or introductory physics classes is, well, if the two forces are equal in opposite direction, why don't they just cancel out? But the reason that they don't cancel out is because the forces are acting on opposite objects, right? So like these two people, push against each other, and will experience a force in the opposite direction. Right? So that's the third law. For every action force, there's an equal reaction force. Right? That's all. One of them you call the action force, one of them call the reaction force. And so the thing about this is, as far as astronomy is concerned, is for the sun, right? Let's think about the sun pulling on the Earth. The sun pulls on the Earth, but the Earth also pulls on the sun with the exact same amount of force, right? So but of course the sun is so much more massive. It's really the Earth that moves around the sun. All right, so there it is. Okay, so this is the universal law of gravitation. All right, so the gravitational force, sometimes just represented as an F, between two objects. Okay, so this is mass, this is capital M, and this is lowercase m. They don't have to be; they can be the same size. Usually when we're thinking about this in terms of astronomy, you have something like a planet or a star is capital M, and then something much less massive, like a satellite or something like that. Or if big M is a star, little m could be a planet. All right. Anyhow, it's any two masses in the universe have a force F, and it's equal to the product of the two masses, capital M times little m, divided by the distance between their centers. Right. So it has to be the distance between the centers squared. And then there's a constant. So this is called the universal gravitational constant. Newton didn't know what that number was. In fact, it was a guy named Cavendish. And in fact, you go to England and there's still what's called the Cavendish Labs. The guy that discovered the electron, so this is, more than a century after this, after Cavendish does this, the laboratories that the guy who discovered the electron, by the way, is named J.J. Thomson. When he discovered the electron, he was working at the Cavendish laboratories. It was just named after him because this was such an important discovery. So Cavendish devised this crazy experiment, which is actually pretty difficult to do, where he literally had these two really large objects, and they brought them close to each other, and he was able to actually measure the force between the gravitational force between them. Gravity turns out to be, you might think gravity is a really strong force, but of all the forces, of the four known forces in the universe, and I'll go over them in just a second, gravity turns out to be the weakest of the four forces. All right, so the next force, the next one that's very common to us is called the electromagnetic force. That's actually one force, by the way, the electromagnetic force. And then there's what's called the weak nuclear force. That's the force that's responsible for radioactive decay. And then, of course, there is the strong nuclear force, the thing that binds protons and neutrons to the nucleus of atoms. All right, so that's the strong nuclear force, and that's the strongest force of them all. So the thing about gravity and electromagnetism is they act over an infinite range, right? So that's and of course with electromagnetism, that only works for things that are charged. If they have a net, so there's an excess positive or an excess negative charge. All right, so with gravity, all you need is mass and the distance between them, the distance between the centers, and so this is big G. So it does have units right here. So the units just make this equation come out right. So the two masses are always in kilograms, and the distance is always in meters. And then remember, you got to square it, and then you use 6.67 times 10 to the minus 11th. So that was Cavendish's number, that he measured more than 200 years ago. Right. So, all right. So that's big G, the universal gravitational constant. All right. So notice, let's say you have a planet going around the sun. And what they do is they approximate of course, we know since the time of Kepler that these are actually elliptical orbits. But they're really almost circles. In fact, that's part of the reason why it was so difficult for Kepler to come up with his laws of planetary motion. Excuse me. When something is traveling in a circle or an ellipse, by the way, it varies slightly with an ellipse. There's what's called a centripetal force that acts on it, and so this is the nature of the centripetal force. It's the mass. So this is the mass on the end of the string. The velocity. So it's actually really the perpendicular velocity. It's perpendicular to a if you drew a line from the center to the object, there would be a perpendicular that would be the velocity would be perpendicular to that, or you could just say that the velocity is tangent to the circle at every point. So down here, the velocity would be going in this direction. So this arrow is constantly changing as the object goes around. And so it's, mv squared over the distance, right? So that's a well-known quantity in physics. And then if you put the two together, right? If you put these two together, you can actually, here, we'll see this right here. So what the purpose of this is, and we're not actually going to do this, okay? So you don't have to do the mathematical steps, but they're just showing you that if you rearrange this and you realize that these objects are going in circles, and the distance that something travels when it goes in a circle is the circumference, which is 2 pi time